Hello, and welcome to this short presentation on an application of reinforcement learning for control. In this presentation, I'll very briefly touch on some things I learned during a 10-week independent study supervised by Professor Leonardo Torres at Cal Poly SLO, in which I tried to use reinforcement learning as a controller of a ball and beam system. Note that this presentation is not intended to be a thorough description of the reinforcement learning process, nor a thorough description of what I did in this project, since it would take much too long. You can, however, find the full 30-plus page report on my LinkedIn and acquire all of the pertinent code I used in this project on my GitHub. The links are shown here below. To begin, why did I ask to perform an independent study focusing on reinforcement learning for control? Well, first, reinforcement learning is another control strategy to have in your toolbox, and for someone interested in systems and control, this is very valuable. There are also parallels to classical control theory that may benefit your overall understanding and learning. Next, reinforcement learning can be used to solve complex problems, such as playing the highly strategic game of Go, as seen in the example of AlphaGo, which I believe beat the Go champion a couple of years ago. And it can be used to create a control policy for very complex systems, such as walking robots. Also, reinforcement learning is a branch of machine learning, which is becoming increasingly popular and is used more and more, especially in the engineering industry. As someone that was on the outside looking in, I thought I would benefit by learning what all the hype was about by doing firsthand. Reinforcement learning has many parallels to classical controls, as is seen in this diagram provided by MATLAB. Notice that the diagrams are color coordinated. This is a very helpful diagram, not only in seeing how each system works, but also how they are analogous to one another. The most important distinction between classical controls and reinforcement learning is the controller and how it is tuned. Whereas a human manually tunes the control policy in classical controls, in reinforcement learning, the control policy comes from an agent, through which the policy is tuned by an algorithm during a training process. Thus, reinforcement learning replaces manual tuning of the controls with automatic tuning of the controls. Key features of reinforcement learning include a reward provided by the environment, a specified set of actions, and a limited set of observations. For those interested, I touched on the reinforcement learning process more in the report I wrote, and there's plenty of great documentation on the internet, particularly, in my opinion, on the MathWorks website if you're interested in implementing reinforcement learning yourself. One of the great things about reinforcement learning is that it is intuitive. Just as living systems may learn a complex routine by reinforcement, so does a machine using an algorithm. This dog, for example, learned to balance on a tightrope by training for about 2 years with an owner. So you'll see the video here. The owner must have devised a coordinated training and reward scheme to get the dog to even attempt balancing on the tightrope, as you're seeing here. After having the behavior reinforced by many trials, the dog eventually understood how to act given different sensory observations in order to receive the reward. In this case, the reward appears to be the ball. Machines, as you'll see in this video, can follow a similar process to learn complex behaviors. MathWorks, for example, provides this example in which they trained this quadruped how to walk by actuating 8 different actuators at each of its joints based on what it was observing at the time. In comparison between the two, the discrepancy in neurons, the things that ultimately determine the control behavior, can be used to explain the discrepancy in complexity. As computing power increases, more and more neurons may be included in the RL agent to achieve more and more complex behaviors in a smaller amount of time. So, in this 10-week independent study, I tried to apply reinforcement learning to this ball and beam system that I had on my own. I developed a software model of the real system I possessed first. So my goal was to create a model of the system in Simulink, train an RL agent virtually on this model, and then deploy this trained agent to the actual hardware. Here is the Simulink model of my system. You can find this Simulink model on my GitHub, along with all of the MATLAB code I used in this whole entire project, by clicking on the link below or pasting it in your browser. This diagram is effectively a reshuffled version of the diagram shown earlier. You'll notice that the key features of my system include a servo actuator and a sensor. These subcomponents need to be accurately modeled for the virtually trained RL agent to be successful when deployed to the hardware. First, to model the servo, I used system identification techniques. I subjected the servo to different inputs. For example, the input shown here when I play this video it was a chirp signal, and I tracked the beam, as you can see here, using MATLAB's computer vision toolbox. I then used MATLAB's system identification toolbox to create different models and see how they fit the experimental data. The different models are shown at the right. In terms of the sensors, I developed a noise model from experimental data. There are many additions to the sensor model I plan in any future work on this project, in which I discuss in further detail in the report. Moving on, a critical element of reinforcement learning is the reward function. A good, correctly tuned reward function plainly delineates good behavior from bad behavior to the agent. A poorly tuned reward function will result in an agent that may be fully trained but not trained to do the desired thing. Perhaps you can think about this better by thinking about how the owner of the dog, the tightrope walking dog, had to tune the reward function to make sure the dog would actually tightrope. In my case, there are two main performance requirements for my reinforcement learning agent. The first, shown at the left, I want the ball to be balanced in the middle of the beam. Preferably, the ball coming to rest right in the middle of the beam after a few seconds would be great. So that's why I rewarded ball positions very close to 0. Second, the reinforcement learning agent must not command the servo to behave in ways that will hurt the hardware or that are impossible to realize. You can see this how I incorporated this performance requirement into my reward function by the plot at the right. Effectively, I penalized large instantaneous changes in servo command, things that the servo cannot actually realize. In terms of the reinforcement learning agent structure, for this project I used a deep deterministic policy gradient agent. A DDPG agent is the simplest compatible agent for use on continuous systems. DDPG agents use an actor-critic algorithm. You can see the actor neural network and critic neural network shown here. In this agent structure, during training, the actor, shown at the left, determines the best action to take based on the feedback it receives from the critic neural network, which is shown at the right. Essentially, the critic uses observations and actions to calculate the expected total reward the agent will see for a single training episode. The actor uses this criticism from the critic to choose the action that optimizes the expected total reward. For my system, both the actor and the critic consisted of relatively small neural networks. Given the simplicity of my control problem as opposed to the walking quadruped, the total number of nodes in both neural networks came out to be 12 as opposed to 1,802 in the example of the walking quadruped. Moving on to training, which is the time-intensive process where the agent acts as the controller during many simulations and the actor-critic neural networks are updated. In my case, the simulation started with the ball randomly positioned between 24 and 16 centimeters away from the center of the beam on either end. The reinforcement learning agent would observe position and velocity from the model or from the environment, I should say, and then manipulate the beam angle and receive a corresponding reward. So in this plot, the blue dots represent the total reward the agent accumulated for that training episode. You can note that the episodes last for as long as 10 seconds or until the ball hits the hard stops of the beam. Thus, the large total reward values around 130 correlate to training episodes in which the reinforcement learning agent balances the ball near the middle of the beam for the majority of the full 10-second episode. The red line is a moving average of the last 50 episode rewards, and when this value reached 120, I set the training session to end, since I had previously determined that the convergent episode reward should be about 130. The yellow line here represents the Q0 value, which MathWorks defines as the estimate of the discounted long-term reward at the start of each episode given the initial observation of the environment. This comes from the critic. In the above figure, if training had been carried on many more episodes and the critic structure was very good, then all three lines would eventually converge. So how did this fully trained agent perform in the model? Looking at this Simulink scope, you can tell a couple things. The first plot at the top shows ball position, which is the actual ball position is shown in black. The sensed ball position being fed to the agent is shown in green. and then velocity using the same sort of color scheme, and then the beam angle at the bottom, where again, the commanded beam angle is in black and the actual beam angle is shown in red. As is shown, the ball position is aggressively corrected at the start of the simulation and eventually oscillates near the middle of the beam. The instantaneous change in beam angle input also appears to be acceptable. So you can tell that the reinforcement learning agent was abiding by the rules of the reward function, so to speak. The major problem, however, with these results is that the servo command also appears to oscillate between its command limits, which is not at all desirable. Ideally, the beam angle would come to rest at 0 degrees, where the ball position was at 0 degrees. Future mitigation strategies may include revisiting the reward function, among many different things. Just to give you a better visual on what this fully trained reinforcement learning agent control policy was, I plotted a surface given position and velocity against beam angle input for both the RL agent and a verified proportional derivative controller, which I verified on the hardware. As you can see, the reinforcement learning control policy has a much more aggressive response to position error and often resorts to commanding this large maxed out beam angle. And this, of course, correlates to the results we saw in the previous shown Simulink scope. Once the reinforcement learning agent policy has been fully validated, it can then be deployed to the hardware for further testing. In some cases, the reinforcement learning agent may even be trained on the hardware. Unfortunately, I moved away from the hardware during the middle of this project and none of the opportunity to deploy a totally satisfactory agent. Nonetheless, I anticipated this might occur and deployed a marginally satisfactory reinforcement learning agent that did converge on a training solution during training. I deployed this to hardware and it gave these results, as you can see in the system or in the video. You can see that this control policy is a lot like the one I just showed, where the reinforcement learning agent chooses to basically just focus on position and command maximum beam angles or the minimum beam angle allowed almost exclusively. Likely, what I think is going on here is several things. I think I need to, there are many things that I talked about in the report, but I think I need better modeling and perhaps a better understanding of reinforcement learning as well. All right, thanks so much for watching. As I said at the start, I hardly covered everything that happened in this project, so I really encourage you to go check out my GitHub and the LinkedIn for the report and the code files that I produced. And I'd like to also thank Professor Leonardo Torres for helping me throughout this 10 weeks. It was a great experience. And just to leave, I came across this quote the other day about learning, so I decided I would leave it with you. All right, thanks so much.